We shall now discuss on module 3 under the banner, that is under the title of the chapter 5 of bounded linear operators. Already we have learned that the BDLXY, the collection of all bounded linear operators from a norm-linear space X to Y, is a norm-linear space. Now, in this module we shall discuss on the convergence of the bounded linear operators, either pointwise convergence or uniform convergence. Now, in this module we shall also learn a famous theorem which is important for functional analysis, that the famous theorem is known as the Banach-Steinhaus theorem. Let us now start with module 3. The title of the module 3 is Convergence of Bounded Linear Operators. Now, we shall start with the collection of all bounded linear operators, that is BDLXY, where capital X and capital Y are two norm-linear spaces over the same field of scalars capital F. The field of scalars may be either real or complex. Let us take Tn, which is a sequence of bounded linear operators from X to Y. Then the sequence of bounded linear operators, that is Tn, converges to T, belongs to BDLXY, that is T is a bounded linear operator from X to Y, and we say the sequence Tn converges to T pointwise or pointwise convergent if limit of n Tnx is equal to Tx. That means, Tnx goes to Tx as n tends to infinity for all x belonging to capital X, which is equivalent to norm of Tnx minus Tx tends to 0 as n tends to infinity. Let BDLXY the collection of all bounded linear operators from X to Y, and Tn be a sequence of bounded linear operators from X to Y. Then sequence Tn is said to converge uniformly to T, which is a member of BDLXY, that is, which is a bounded linear operator from X to Y if norm of Tn minus T tends to 0 as n tends to infinity. Here norm of Tn minus T tends to 0 as n tends to infinity taken in the sense of the operator norm, that is norm of T equal to supremum of norm of x less or equals to 1 norm of Tx, or norm of T equal to supremum of norm of x equal to 1 norm of Tx, or norm T equal to supremum of x not equal to 0 norm of Tx by norm of x. So, in this connection we get a remark. So, given a sequence of bounded linear operators from X to Y, that is, if we consider the sequence of operators Ti taken from BDLXY, if supremum of I norm of Tix less than infinity for all x belongs to capital X, means it is pointwise bounded on capital X, and supremum of norm of Ti less than infinity means it is uniformly bounded. Thus, right now we have learned the sequence of bounded linear operators which is pointwise convergent, and also we have learned the sequence of bounded linear operators converges uniformly to a bounded linear operator T. Now, at this moment we have learned sequence of operators is pointwise bounded, sequence of operators is uniformly bounded. Note that uniform boundedness implies pointwise bounded. Indeed, if supremum of I norm of Ti less than infinity, if we consider that uniform boundedness for a sequence of operators holds. So, that is why we have assumed that supremum of I norm of Ti less than infinity. So, there exists a constant m greater than 0 such that norm of Ti is strictly less than m for all I equal to 1 to up to so on. So, here norm of Ti is strictly less than m may be assumed norm of Ti less or equals to m. So, for each fixed x belonging to capital X, norm of Tix less or equals to norm of Ti into norm of x, because Ti are taken from BDLXY. So, norm of Tix less or equals to norm of Ti into norm of x, as we have assumed norm of Ti less or equals to capital M. So, norm of Ti into norm of x less or equals to m into norm of x for all x belonging to x where x is taken fixed, and for all I equal to 1 2 and so on. Thus, we get norm of Tix less or equals to m into norm of x. This implies that supremum of I norm of Tix less or equals to m into norm of x. Here supremum is taken over all I equal to 1, 2 and so on. Thus, we have supremum of I norm of Tix less than infinity, which implies that Ti is pointwise bounded. But converse is not generally true, but the converse is true if capital X is complete. So, in this connection we have a important theorem which is the pillar of the function analysis. There are 4 pillars in function analysis. Number 1, this is the Banach-Steinhaus theorem. Already we have learned the Hahn-Banach theorem, also we have learned the closed graph theorem and also open mapping theorem. Whole functional analysis is based on the 4 theorems. So, we shall now discuss on a very important theorem which is known as the Banach-Steinhaus theorem. So, the statement of Banach-Steinhaus theorem is that let capital X and capital Y be 2 norm-linear spaces over the same field of scalars capital F such that capital X is complete. Let Ti be a sequence of bounded linear operators from capital X to Y satisfying supremum of I norm of Tix less than infinity. That is, supremum is taken of all norm Tix for each x belongs to capital X, then supremum of I over Ti less than infinity. The proof goes below. For each positive integer n, let us consider a set Fin. That is, Fin is the set of all elements for which norm of Tix less or equals to capital N. Clearly, the sets Fins are non-empty, because we have assumed in the statement that supremum of norm of Tix and supremum is taken over I is strictly less than infinity. That is, supremum of I of norm of Tix is bounded. So, that is why Fins are non-empty. Also, each Fin is closed. So, in order to prove that Fin is closed, we have to prove Fin bar is equal to Fin. So, if we can show that Fin bar is a subset of Fin, and we know that Fin is a subset of Fin bar, and we get Fin bar equal to Fin. So, we start with x belongs to Fin bar. So, there exists a sequence of elements xr belonging to Fin such that xr goes to x as r tends to infinity. Since each Ti is continuous, because Ti are bounded linear operators from x to y, and already we know that every bounded linear operator is continuous. So, hence each Ti is continuous. So, xr goes to x as r tends to infinity implies Ti xr goes to Tix. So, norm of Tixr goes to norm of Tix as r tends to infinity, because norm function is continuous. Now, norm of Tixr less or equals to n, because xr is taken from Fin, and Fin is assumed the collection of all elements for which Tix less or equals to n. So, limit of r norm of Tixr less or equals to n. Thus, norm of Tix less or equals to n implies x belongs to Fin. So, Fin is closed, and hence Fin bar equal to Fin. So, Fn is equal to intersection I equal to 1 to infinity Fin is non-empty, a closed subset of capital X, because theta belongs to each Fin. So, intersection of I equal to 1 to infinity Fin contains the 0 element, at least the 0 element theta, and we know that intersection of closed sets is again a closed set. So, Fn is a closed subset of capital X. Now, Fn is equal to I equal to 1 to infinity Fin is equal to collection of all such elements taken from X, that is collection of all elements x belonging to capital X for which Tix less or equals to n for all I equal to 1, 2 and so on. Now, we claim that capital X is equal to union of Fn. For let x belongs to capital X, since supremum of norm of Tix and supremum is taken over I which is less than infinity. So, there exists n such that supremum of I norm of Tix less or equals to n, that is Tix less or equals to n for all I equal to 1, 2 and so on. So, x belongs to capital Fn implies x belongs to union I equal to 1 to infinity Fn. We have started with an element x belongs to capital X. So, x is a subset of union of I equal to 1 to Fn, and each Fn is a subset of x and union of I equal to 1 to infinity Fn is a subset of x. So, we get x equal to union I equal to 1 to infinity Fn. Since capital X is complete, by Bayes category theorem there is at least one member say Fn naught of sequence of sets Fi which is not nowhere dense in capital X, because Bayes category theorem states that every complete metric space is not a set of first category, that is every complete metric space is a set of second category. So, here we shall apply the Bayes category theorem. So, that is why there exists at least one member say Fn naught of sequence of sets Fi which is not nowhere dense in capital X. Since Fn naught is closed, we find a closed sphere Sr naught x naught, that means a closed sphere centered at x naught with radius r which is always within the set Fn naught, because interior of closure of Fn naught is non-empty. This implies interior of Fn naught is non-empty as Fn naught is closed, that means Fn naught equal to Fn naught bar. So, norm of Ti of closed sphere Sr x naught is less or equals to n naught for all I. Now, we shall calculate Sr x naught minus x naught, that is Sr x naught minus x naught is equal to collection of all such elements x minus x naught belongs to capital X, where x belongs to Sr x naught, which is again equals to collection of all such elements x minus x naught belonging to capital X, for which norm of x minus x naught less or equals to r by the definition of the closed sphere, which is again equals to y belongs to capital X, for which norm of y less or equals to r, where y is taken as x minus x naught. So, 1 by r of collection of all such sets Sr x naught minus x naught is the closed unit sphere centered at 0 vector of capital X. Further, if u belongs to 1 by r of the set Sr x naught minus x naught, then u equal to x minus x naught by r, where x belongs to Sr x naught, that is the closed sphere centered at x naught with radius r, that means norm of x minus x naught less or equals to r. So, thus if u belongs to 1 by r of set Sr x naught minus x naught, then u equals to x minus x naught by r. So, norm of Ti u equal to norm of Ti of x minus x naught by r, where u equal to x minus x naught divided by r is assumed and x is taken from Sr x naught. So, norm of Ti of x minus x naught by r is less or equals to 1 by r norm of Ti into x minus x naught, which is again less or equals to 1 by r norm of Tix plus norm of Tix naught by the triangle inequality property of the norm axiom, that is third norm axiom, which is again less or equals to 2 n naught by r, where 1 by r of norm of Tix plus norm of Tix naught less or equals to 2 n naught by r. So, norm of Tiu less or equals to 2 n naught by r. So, supremum of u belongs to 1 by r of set Sr x naught minus x naught of norm of Tiu less or equals to 2 n naught by r, that is supremum is taken over all such elements u taken from the set 1 by r into Sr x naught minus x naught, which implies that norm of Ti less or equals to 2 n naught by r, which again implies that supremum of norm of Ti over I less or equals to 2n naught by r, but 2n naught by r is less than infinity. This means supremum of norm of Ti over I less than infinity, that is norm of Ti are uniformly bounded. Now, in this connection we take a note that this theorem is known as uniform boundedness principle theorem. Up to this, in module 3 of this chapter 5, we have learned the convergence of a sequence of bounded linear operators. Also, we have learned a famous theorem, the Banach-Steinhaus theorem or uniform boundedness principle theorem. Now, we shall discuss on application of uniform boundedness principle. Also, in this connection, also we shall learn if sequence of operators converges to a bounded linear operator and sequence of operators is totally bounded, then T, that is the limit point of sequence of operators, is again a bounded linear operator from x to y. Now, let us take a theorem. If Tn is a sequence of bounded linear operators from a nonlinear space capital X to a nonlinear space capital Y, converging pointwise to the mapping T from capital X to capital Y, and if sequence Tn is totally bounded, that means there exists a constant m greater than 0 such that norm of Tn is less or equals to capital M for all n, then T is a bounded linear operator from X to Y, that is T belongs to BD LXY. The proof is given below. Since Tn converges to T pointwise, we have limit of Tnx and limit is taken over n is equal to Tx for all x belongs to capital X. Let x comma y belonging to capital X. We shall now show that T is linear. So, for this we now calculate T of x plus y is equal to limit of n Tn x plus y, because Tn is pointwise convergent to a mapping T x to y. So, limit of n Tn x plus y is equal to limit of n Tn x plus limit of n Tn y, which is equal to Tx plus Ty. Similarly, for any scalar alpha belonging to capital F, either the field of scalars may be real or may be complex, we have T of alpha x is equal to alpha of Tx. So, we see that capital T is linear. As sequence of norm of Tn is totally bounded, there exists a positive constant capital M such that norm of Tn is less or equals to capital M for all n. Now, for each x belonging to capital X, norm of Tnx less or equals to norm Tn into norm of x. This is due to the fact that Tn is a sequence of bounded linear operators. So, that is why we have written norm of Tnx less or equals to norm Tn into norm of x. As norm of Tn less or equals to m, so we have norm of Tn into norm of x less or equals to m into norm of x. So, limit of n norm of Tnx less or equals to m into norm of x, which implies that norm of Tx less or equals to m into norm of x. This shows that T is bounded. Now, let us take another theorem. Let X be a Banach space, that means X be a complete norm-linear space and Y be a norm-linear space over the same field of scalars capital F. The field of scalars F may be either reals or may be complex. If sequence Tn is a sequence of bounded linear operators from capital X to Y, that is sequence Tn is taken from BDLXY such that Tn converges to T pointwise, then sequence Tn is totally bounded and T is a bounded linear operator from X to Y, that is T belongs to BDLXY. The proof is given below. Since Tn converges to T pointwise, so for each x belongs to x, limit Tnx is equal to Tx for all x belongs to capital X. So, Tnx is a bounded sequence in capital Y. We know that every convergence sequence is bounded. So, supremum of norm of Tix and supremum is taken over I is straightly less than infinity. So, supremum of I norm of Ti less than infinity by uniform boundedness principle, because we have assumed that capital X is a Banach space. Hence, there exists a constant capital M greater than 0 such that sup of I norm of Ti less or equals to M, that is norm of Tn less or equals to M for all n, because norm of Tn is less or equals to supremum of I over norm of Ti, and supremum of I norm of Ti less or equals to M, it follows that norm of Tn less or equals to M for all n, and this shows that sequence Tn is totally bounded, and hence T belongs to BD LXY. So, there is an application of uniform boundedness principle. So, the assumption of the completeness of the space, that is nonlinear space capital X, to be complete. So, in this case we shall cite an application that if X is not complete, then the result, that is the statement of the uniform boundedness principle, does not hold. So, let us take an example. Nonlinear space curly P of all real valued polynomials with norm P equal to maximum of mod Aj, and maximum is taken over J, where P is taken from the collection of all polynomials with Pt is equal to A0 plus A1t plus A2t square plus dot 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 plus An t to the power n, where Ai's are reals, is not a Banach space. It follows by applying uniform boundedness principle theorem, we can take P belongs to curly P in a form Pt equal to A0 plus A1t plus A2t square plus An t to the power n, where An is not equal to 0, and this is equal to A0 plus A1t plus A2t square plus dot 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 plus An t to the power n plus An plus 1 t to the power n plus 1 plus dot 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 and so on, with An plus 1 equal to An plus 2 equal dot 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 equal to 0, and that can be written as sigma k equal to 1 to infinity ak t to the power k. It does not matter if Pt is the 0 polynomial. Now, define a sequence of functionals Fn in the following way: Fn of 0 polynomials is equal to 0, and Fn P is equal to A0 plus A1 plus A2 plus dot 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 plus An minus 1, where P is not a 0 polynomial. Clearly, for each n, Fn is linear and each Fn is bounded, because modulus of Aj is less or equals to norm of P. So that modulus of Fn P less or equals to n into norm of P. Furthermore, for fixed P belongs to curly P, that is the collection of all polynomials having under consideration, sequence Fnp satisfies modulus of Fnp less or equals to nx plus 1 into maximum of modulus of Aj, and maximum is taken over J, where nx is equal to degree of P, where P is the polynomial. That means, for each P belongs to curly P, sequence Fn is bounded. However, we will show that sequence Fn is not norm bounded. As for example, let us take a polynomial Pt equal to 1 plus t square plus dot 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 plus t to the power n. So, norm of P equal to 1, because all the coefficients in this polynomial is equal to 1, and norm is taken over maximum of modulus of the coefficients. Here the coefficients are 1. Now, Fnp equal to 1 plus dot 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 plus 1 n terms is equal to n into norm of P. Now, norm of Fn less or equals to modulus of Fnp divided by norm of P, because P is not a 0 polynomial, and which is equal to n, where n is free to take indefinite large values. Clearly, sup of n norm of Fn equal to plus infinity. Hence, uniform boundedness principle theorem is failing. So, collection of all polynomials is not complete. In this module 3 of chapter 5, we have learnt so many properties of the convergence of sequence of the bounded linear operators. Also, we have learnt on a theorem, Banach-Steinhaus theorem, called uniform boundedness principle theorem. Also, we have learnt an application of Banach-Steinhaus theorem. With this, we come to an end of the module 3 of chapter 5, and also we now close the chapter 5.